All right, so I know the first part of section 7.6 Bayes Thm was a really long video. I promise this one won't be anywhere near as long. I know that because there's only one page. It's the only problem that's going to be in this video. All right, so let's take a look at this problem. Let's read the problem, and then we'll go through it and see how we can solve this problem. It reads, it has been estimated that along a certain stretch of highway, approximately 1 out of 500 cars will be carrying illegal drugs. Police agencies using narcotic sniffing dogs to search for these drugs. Research has shown that the drug sniffing dogs will provide a false positive result at a 10% rate and will provide a false negative at a 5% rate. Suppose that a drug sniffing dog alerts on a randomly selected car. What is the probability that the car is carrying illegal drugs? All right, so first off, there may be some phrases or some terms in here you're not comfortable with, like this. A false positive rate. What does it mean to say that it is a false positive? Well, a false positive is when the test result comes back positive, but it shouldn't have. So in this case, that would mean that we're talking about a probability of something being 10%, where it's a false positive, meaning that the drug dog alerted on the car, but there were no drugs. Okay? And so if we go with some logic here, we say that A means the dog alerted, and D means that there are drugs in the car, then I can write this as, come on, there we go. The probability of A given D complement is equal to 10%. A conditional probability that the dog alerted giving a positive result, but it's a false positive because there were no drugs in the car. If I use that exact same logic, that means that a false negative would mean that the dog didn't alert when there were drugs in the car. A false negative means that you got a negative test result, but you shouldn't have. So the dog didn't alert when they should have. Okay? All right, so that's what those phrases, that's what those terms mean. So let me get rid of this because we're going to need this space. But I just want to make sure, because some people have familiarity with that kind of stuff, some people don't. It just depends on what classes or what education you've had up to this point in probability. Okay? All right, so my job is to solve this question, that if a dog alerts on a car, what's the probability that they're carrying illegal drugs? So what's the probability that there are drugs in the car given that a dog alerts? That's my job. Okay? So the first thing I'm going to do is I'm going to start building this tree diagram. Well, I know that the first branch has to be about whether there are drugs or not drugs in the car, because those conditional probabilities that we talked about a little bit ago all require that we know whether the car has or does not have drugs in it. And then the second branches are going to be the dog is going to alert, given that there are drugs. The dog won't alert, given that there are drugs. The dog will alert, given that there are not drugs. That's supposed to have a complement on it. And the dog won't alert, given that there are not drugs. Now, in the grand scheme of things, this right here and this right here, the top branch and the bottom branch are the only two branches of this diagram here that actually are true results. These two in the middle here, these two branches here, those are our falses. The top one is our false negative because it's a didn't tell me I had drugs when I should have. And the bottom one's the false positive because it's a did tell me I have drugs when I don't. All right, let's start putting some probabilities on this. I know that this is 1 out of 500 because it said so in the problem, 1 out of 500 cars, which means this is 499 out of 500. I know that my false negative here is 5%, 0.05. Okay, I'm actually going to rewrite that so I can see it a little better. 0.05, and that makes this a 0.95. Okay? I know that my false positive is at a 10% rate, which means this is a 0.90 or 90%. Right? Now, if my job is to find the probability of D given A, that is the flip or the inverse of the conditional probabilities given to me in the problem. So that means this is a Bayes theorem problem, right? So I'm going to set it up over here as a Bayes theorem. So the probability of D given A is going to be equal to the probability of A times the probability, probability of D, I read that wrong, times the probability of A given D divided by the probability of D times the probability of A given D plus the probability that you don't have drugs times the probability that the dog alerted given that you don't have drugs. Okay. So the probability of D given A, and I'm going to put all those numbers in for this. So drugs was 1 out of 500 times alert given drugs, that's the times the 0.95 from that first branch up here. All right. And then I've got that same thing downstairs times 0.95 plus, and plus don't have drugs, so 499 out of 500 times alert given don't have drugs, so that's the 10%. Okay. And now I'm going to take this hot mess right here, throw this in my calculator and see what happens. Okay. So I'm going to make a fraction. Numerator is going to be 1 divided by 500 times 0.95. My denominator is going to be that 1 divided by 500 again, times that 0.95, plus that 499 divided by 500 times 0.1. And I press enter, and I get 2%. Rounded 2%, 0.0186, so 2%. Wait a second. So you're telling me that if a drug dog alerts on my car and there is no other reasons to think that there are drugs in that car, that just based solely on that drug dog alerting on my car, that means that there's only a 2% chance that there actually are drugs in my car? Is that what you're saying? Let's check the math, make sure we did this right. Bayes' theorem says if you want the probability of D given A, find the probability of D times AD over D times AD plus D complement times AD complement. 1 out of 595, that looks good. 1 out of 595, that's good. 499, 10, that's good. Yep, that's correct. Okay. So Bayes solely, is that how you spell solely? Oh, it doesn't look right. Bayes only. All right, now I don't want to get political here because that's not what this class is about, but these numbers right here, I got those from the national leading trainer of drug dogs. So those are real numbers. I had to make this up because I have no idea how many cars have drugs in them. That's not a world I live in. But I got those 95, 5, 10, and 90% here. I got this information from the drug dog trainers themselves, the actual people who do this. All right? So this is real. This is true. Right? And this is why Bayes' theorem is said to be so powerful. Right? This number right here, this 95%, that's the number that the drug dog people say. They say, we are 95% accurate. And they are. If there are drugs in the car, there's a 95% chance they'll find them. they also cite this number down here, and they say that we are 90% sensitive. And sensitive means that we won't give you a positive result if we shouldn't. And that is accurate. But based solely on the drug dog itself and no other indicators whether there are or are not drugs in the car, having the drug dog alert is not a very high chance that there will actually be drugs in that car. This is why Bayes' theorem is powerful, because if you're in the jury, if you're on the jury, and the evidence being presented to you is, well, the drug dog alerted on the car, so we knew there were drugs in the car, and the drug dog is 95% accurate, well, a logical person would look at that and go, oh, okay, so they had probable cause or whatever it is. But the reality is it's not true. And Bayes' theorem shows that. Bayes' theorem shows the power of that. Right? There are lots of examples for this. There are hundreds and hundreds of examples that are similar to this, where the outcome is exactly the opposite of what you would think. You would think there's a high probability of something occurring when there's actually a low probability. And so Bayes' theorem shows up. They hire people to come into court to explain Bayes' theorem to people because it's so often misinterpreted, misused, misunderstood. Right? There's an entire field of study called Bayesian statistics where they take a look at this kind of thing and how it applies across all different fields. Anyway, you'll run into this again. I can guarantee you that Bayes' theorem will show up somewhere else in your business education. All right, so that brings us to the end of 7.6, also to the end, honestly, of Chapter 7. So we're done with probability, Chapter 7. We'll move on to Chapter 8. In Chapter 8, we're going to continue down this path of probability, but the problems are going to get a little more complicated. I know you're thinking, how could they get more complicated than this? More complicated because the events and the sample spaces are going to get bigger, harder to count. All right, have an amazing day. I'll see you all when I see you.